Hey everyone, my name is Charles, and this is a preview of our work, Convex and Bilevel Optimization for Neurosymbolic Inference and Learning. And I'm super excited to be presenting this work at ICML in Vienna this year. So NESSE is a line of research which aims to create a synergy between two complementary machine learning paradigms, neuro and symbolic. And NESSE is a highly active field with new tools being proposed every year at the top machine learning venues. We make use of a framework called NESSE EBMs, and this is a mathematical foundation for NESSE. And simply put, NESSE EBMs are compositions of neural and symbolic components that define an energy function to quantify the compatibility of variables. Predictions from an NESSE EBM are variables with the highest compatibility or lowest energy. And these predictions are obtained through an optimization process that minimizes the energy function. And this inference process in an SEBM is where reasoning happens. This is where we can point to and say where constraints are being enforced and our system is being controlled. And to state the obvious, NESSE-EBM learning is finding weights that lead to more correct predictions. For NESSE-EBMs, this means finding weights that assign lower energies to more correct predictions or the training data. What's less obvious is finding principled gradients for NESSE-EBMs, since predictions are obtained through this complex optimization process that might not permit trivial applications of automatic differentiation. For example, backpropagating through an optimization process can accumulate errors, or it might not even be possible if there's non-differentiable operations that are being performed. And this challenge is one thing that connects NESSE to the broader machine learning community. Specifically, we see this same challenge come up in meta-learning, hyperparameter optimization, and learning with mathematical programming layers. And in this work, we pose the problem of NESSE-EBM learning as bilevel optimization. Intuitively, the upper level objective is a learning loss that encourages predictions to be close to the training data, while the lower level objective is NESSE-EBM inference or reasoning. Now, I'm not going to go into the details, but the main ideas we introduce to achieve scalable end-to-end NESSE-EBM learning is the use of a bilevel value function reformulation, a smoothing technique that substitutes the energy function with its Morrow envelope to ensure finiteness and differentiability, and a relaxation of the problem constraint to ensure convergence properties. We implement our learning algorithm and analyze it in NewPSL, an expressive and open source NESSE library that supports prediction with hard and soft logical and arithmetic constraints. Additionally, we advance NewPSL theory with a reformulation of inference program as a convex, linearly constrained quadratic program, and this has multiple advantages. Theoretically, we can use the LCQP to establish continuity properties of NewPSL that ensure principled end-to-end gradient-based learning. And the new formulation motivates a primal dual block coordinate descent inference algorithm that produces the statistics we need for computing learning gradients, and it leverages warm starts, which we show is vital for improving NESSE learning runtimes. We perform an extensive empirical analysis across 8 datasets with varying tasks and corresponding model properties. And I only have time to highlight some of our results, but we see over 100 times speedups in NESSE learning runtimes and a consistent performance improvement using our bilevel learning algorithm. I'm super excited to be presenting this at the poster session. I'll be presenting it on Wednesday during session 3 at 11:30 to 1 p.m. in Hall C, and I'll be poster number 406. Okay, see you then. Thanks.